Yeah. Good evening, my dear students. How are you, all of you? Studying well? Yeah. TS EAMCET is coming close to you. It is in front of you, almost in front of you.
2 weeks.
So, only 2 weeks. Today, I am going to start chemical bonding. Solid state, so many numericals are there. Based on my explanation, you can do so many questions, no doubt. So I said all techniques also, how to approach easily everything. Now I want to start chemical bonding. Sir, where is the... No. Yes, sir. See, chemical bonding. So in the formation of a bond, potential energy of bonded atoms are decreasing. Right? So, wait. Just wait, my dear students. Amma, Srilata, good evening. Sridevi, good evening. Koteswar Rao, yeah. Chemical bonding. Now directly I want to discuss about ionic bond. Ionic bond. Yeah. What is the meaning of ionic bond? It is strong electrostatic force of attraction between two oppositely charged ions. In the formation of ionic bond, electron is traveling from one atom to another atom. Positive charge, negative charge. So this attraction is called ionic bond. Now favorable conditions for the formation of ionic bond. Listen very carefully. Favorable conditions for the formation of cation. First condition, large size. Large size. Second, low ionization potential. TS EAMCET 24th August na. Amma Sridevi. And third, low ionic charge. Low ionic charge. And fourth condition, cation. Now, large size. See once again. If you consider lithium, sodium, potassium, rubidium, and cesium, size of atom increasing. So, this is called most ionic. Most ionic. And this is called strong ionic. Strong ionic. What is the difference between most ionic and strong ionic? If you consider lithium fluoride strong ionic, if you consider cesium fluoride most ionic. Most ionic. Now, this is strong ionic. Why? Definitely you are having a doubt. Now, ionic strength is equal to 1.44 into Z plus Z minus by radius of cation plus radius of anion whole square. This is called ionic strength. Now, if you consider lithium fluoride, lithium ion is having 1 angstrom, fluoride also 1 angstrom. I am saying consider. Consider. If you consider cesium fluoride, size of cesium 5 angstrom, fluorine 1 angstrom, fluoride. Now 1.44 into Z plus Z minus by 1 plus 1 whole square. So 1 by 4 into Z plus into Z minus. Now if we consider cesium fluoride 1.44 by 5 plus 1 radius of cation plus radius of anion whole square. So what is that? Radius of cation 5 plus 1 whole square into Z plus Z minus. Therefore, 1.44 by 36 into Z plus Z minus. Now, comparison to this value, it is more, it is less. Therefore, lithium fluoride is strong ionic. Lithium fluoride, strong, ionic. Cesium fluoride, most ionic, Understood? All of you understood? Good evening, Karan Sai. Okay. Now look here. This is about formation of ionic bond. Now first condition, large size. First condition, what is the first condition? Large size. Favor formation of ionic bond. Second condition, low ionization potential. Third condition, low cationic charge. Fourth condition, cation with octet forms ionic bond. Example, Na plus, Cl minus, 2s2, 2p6 and calcium chloride, Ca plus 2 and 2Cl minus. Ca plus 2 is having 3s2, 3p6. Understood? So, calcium chloride is ionic. And if you consider zinc chloride, zinc plus 2, this is having 3s2, 3p6, 3d10. So, such kind of configurations are called pseudo-inert gas configuration, pseudo-octet. So, such molecules are forming covalent bonds. Yeah. Now, see, in this periodic table, if you go like this, right, Cu, copper, silver, gold, zinc, cadmium, mercury, all these are exhibiting pseudo-octet configuration. So they are all forming covalent compounds. Now, another example. If you consider sodium chloride, magnesium chloride, aluminum chloride, and silicon tetrachloride. Here charge of cation plus 1. Here charge is plus 2, charge plus 3, plus 4. So, if the charge of cation, cation charge increases, covalent character increases. So, silicon tetrachloride is most covalent. You can apply same concept to any compounds. If you consider PCl3 and PCl5, which is most covalent, oxidation number plus 3 plus 5, because with increase of oxidation number, polarizing power increases. Covalent character increases. If polarizing power increases, covalent character also increases. Now another favorable conditions for formation of an ion. Favorable conditions for the formation of an ion. If you consider F minus, first one, low ionic charge. Low ionic charge among F minus, O minus 2, N minus 3. F minus forms most ionic. N minus 3 forms mostly covalent. Okay. So, first condition, low anionic charge. Low anionic charge. Favor ionic character. Second condition, anion. Second condition, anionic. No. Sorry. Second condition, small size of an ion. Small size of an ion among F minus, Cl minus, Br minus, I minus. F minus easily formed. Because size is small, ability to attract electrons increases. If I am considering HF, that is different. If I am considering sodium fluoride, it is mostly ionic. You can understand silver fluoride, silver chloride, silver bromide, silver iodide. So this is most ionic. This is most covalent. Why? Because if the size of an ion increases, polarizability, ability to give electron increases. So as size of an ion increases, polarizability increases. Covalent character increases. Similarly, third condition, high electronegativity and high electron affinity. It is the third most favorable condition for the formation of ionic bond. So, electron affinity much dominating comparison to electronegativity. So, if you consider fluorine, chlorine, bromine, iodine. Now, what is happening now, my dear students? Tell me, electronegativity of fluorine greater than chlorine than bromine than iodine. So, it is most ionic. It should be most ionic. And if you compare electron affinity, chlorine greater than bromine than iodine. If you are comparing chlorine, bromine, iodine. Now, which has high electron affinity, chloride is having high electron affinity, chlorine is having high electron affinity. If high electron affinity, that should form most ionic bond. Therefore, among NaF, sodium chloride, most ionic. Which is most ionic? Can you please tell me why? Which is most ionic? Sodium chloride should be most ionic, but not sodium fluoride. Why? Because polarizability of chloride is more than fluoride. Therefore, sodium fluoride is more ionic. This is more ionic than sodium chloride. It's very important. Yeah. Now, I will discuss about properties of ionic compounds. All properties I will say orally. What I am saying, ionic compounds are right very hard due to strong electrostatic force of attractions. Strong electrostatic force of attractions. Next, ionic compounds are soluble in polar solvents like water. Why? Dielectric constant is more, then solubility is more. Understood? It's very important. Listen very carefully, all of you. So, dielectric constant of hydrogen sulfuric acid, more than hydrogen peroxide, more than water, like that, dielectric constant. Now, water is only used as a solvent. We should not use them as solvent because sulfuric acid and hydrogen peroxide are strong oxidizing agents. So we should not use them as solvent. Understood? Okay? Yeah. Next, ionic compounds do not show isomerism. Why? Because ionic bonds are non-directional bonds. Ionic bonds are non-directional. What is the meaning of non-directional? If you consider sodium ion having attractions same in all directions. Attractions are same in all directions. Therefore, this is non-directional bond. It will not show space isomerism. Means geometrical and optical it will not show. Okay, and also structural also it will not show. Very important question. Similarly, ionic compounds are soluble in polar solvents. Why? Because in polar solvent these are hydrated. Why hydrated? Due to interaction of oppositely charged ions. Means if you consider water, oxygen, hydrogen, and hydrogen. This is called water. Okay. So in this water, negative charge is present on oxygen. It is attracting sodium ions. It is attracting sodium ions. Understood? Yeah. Now, like that, there are ionic compounds, good conductor of electricity, good electrical conductor, good electrical conductors in molten state and in aqueous solution due to questions. Whatever sentences I am speaking, they are all questions only. Listen very carefully. Due to free ions, because if you take sodium chloride solid, when it is on strongly heating, it is giving Na plus ion, Cl minus ion. So these are free ions. Option free electron also there. It is not correct. Okay, only free ions. Now, solubility of lithium fluoride, lithium chloride, lithium bromide, lithium iodide. Solubility. So, it is most ionic. This is most ionic. And this is most covalent. So, now, which is considering as most soluble in water in this case? If cation is small, it is also small. This is also small. Okay. Here, lattice enthalpy, lattice energy of lithium fluoride is maximum. Comparison to lithium iodide. Therefore, lithium iodide is more soluble. Because loose packing. These are strongly packed. Strong packing, strongly attracted. So, solubility of fluorides least for lithium only. Now tell me, which is most soluble in water? Lattice energy inversely proportional to solubility. Exactly. Lattice energy inversely proportional to solubility. Generally, but except to lithium fluoride. Generally, solubility or lattice energy inversely proportional to solubility. It is only general. Exception to lithium fluoride. And one more point I am saying, all of you listen very carefully. In case of alkali and alkaline earth, metal, fluorides and hydroxides, solubility decreases. Solubility increases from top to bottom. It means lithium fluoride is least soluble, then sodium fluoride, then potassium fluoride, rubidium fluoride, cesium fluoride, like that. Beryllium fluoride, then magnesium fluoride, then calcium fluoride, right? Then strontium fluoride, barium fluoride. Solubilities are increasing from top to bottom. In case of hydroxide also, same order. Why? Because reason, if anion is smaller, like F minus OH minus, then lattice enthalpy decreasing is more. Lattice enthalpy decreasing is more compared to decrease of hydration enthalpy. What does it mean? It means that, right? What does it mean? Look, if you consider beryllium fluoride, calcium fluoride, like that, barium fluoride. Here lattice enthalpy, lattice energy, for example 900, here 700. And if you consider hydration enthalpy, it is also liberated minus 900. Here it is minus 800. So in which case lattice enthalpy much decreasing? In this case, decrease of lattice enthalpy more, gap is more comparison to this gap, right? Kiran Sai, what increases from top to bottom? Lattice enthalpy inversely proportional to solubility, okay. But here you have to understand very clearly. Similarly, if anion is large, like if anion is large, like carbonate and sulfate, if you consider so beryllium carbonate and beryllium sulfate, magnesium carbonate, magnesium sulfate, like that, barium carbonate, barium sulfate. Now What I am saying here, if the size of anion is large, if size of anion is large, then lattice energy is much smaller, but hydration energy decreases from top to bottom. Therefore, solubility decreases. Sir, 1 minute. So, here, this is about the key point. Okay, done. Now, I want to discuss about lattice energy.
Sorry,
That students streaming
మీరు క్లోజ్ చేశారు.
క్లోజ్ అంటే ఇక్కడ
ఏదో ఒకటి తగిలిందంటే పోతుంది. సరే మీరు చెప్పుకుంటూ వెళ్ళిపోండి.
lattice energy. What is the meaning of lattice energy? See, if you consider sodium and chloride, which are at same distance, so the energy liberated is equal to minus U. If you consider Mg plus 2 and O minus 2, both are at same distance, then the energy liberated in second case equal to minus 4U. Therefore, lattice enthalpy depends upon charge of cation and anion. If you consider aluminum ion and nitrate ion, right, you are expecting minus 9U, may be correct. If you consider aluminum oxide, in this case, we have to consider 2 mole of aluminum, 3 mole of O minus 2, 2 into 3, 6, nearly 36 times. Therefore, lattice energy of aluminum oxide greater than aluminum nitride greater than magnesium oxide greater than sodium chloride. Listen very carefully. 99.99% of every class, they are saying aluminum nitride is more lattice enthalpy comparison to aluminum oxide. 100% wrong. Be careful. This is only more. You are objecting me. Sir, aluminum is having a charge plus 3, oxygen minus 2, 3 into 2, 6 units. Aluminum is having a charge plus 3, N minus 3, 9 units. Like that, you may ask me. I am saying, no, it should not be like this. Okay? Yeah. Telugu Academy textbook, doing previous 5 years questions for TS EAMCET is enough. Yes, Amma, it is enough. Along with that, it is enough, but one point I want to say, whatever grandest papers you are writing in your college, that you have to solve and then update. It is enough. Enough means See, if you want to get full marks means you have to go through full material. In which college you are studying? Syed, okay, Junad, okay, yeah. Now look here. That is fine. What is fine? Aluminium. This is the decreasing order of lattice energy. Over. Now I want to discuss about covalent character, covalent bond. Covalent bond. It is the bond formed by mutual sharing of bonded electrons. We can call it as covalent bond. See, in the formation of fluorine and fluorine. Here 7 electrons, 1, 2, 3, 4, 5, 6, 7. Another one, another fluorine I want to see. What is that? See, 1, 2, 3, 4, 5, 6, 7. This is 7 electrons and it is also 7 electron. So total how many? Sharing how many? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Total 8. So it is octet. Like that, you have to say formation of ozone, oxygen, oxygen. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 electron coming here. Why? This has to satisfy octet and this has to satisfy octet. This oxygen also has to satisfy octet. So every atom is satisfying octet. So it is atom A, atom B, atom C. Now formal charge is equal to, what is the meaning of formal charge? Number of valency electron minus number of non-bonded electrons minus 1 by 2 into number of bonded electrons. It is called calculation of formal charge. Now listen very properly here. If you consider this oxygen, this is atom A, atom B, atom C. Formal charge of A. How to calculate number of valency electron? Oxygen 1s2, 2s2, 2p4. These are valency electron. So number of valency 6 minus number of non-bonded. These are called non-bonded 1, 2, 3, 4 minus 1 by 2 into number of bonded electrons. These are bonded 1, 2, 3, 4. So finally what you are getting now? 6 minus 4 minus 2, 0. So formal charge of atom oxygen, atom A 0 and atom B, like that you try, you will get +1. It is -1. Similarly, what is the formal charge of phosphorus and oxygen in phosphate? Formal charge of phosphorus and all oxygen atoms is how much? In order to calculate the formal charge of phosphorus, central atom has to show octet. So write phosphorus. Valency electron 3s2, 3p3, 5. 1, 2, 3, 4, 5, and oxygen 1, 2, 3, 4, 5, 6. Another oxygen 1, 2, 3, 4, 5, 6, 7, 7. So minus charge. Another oxygen 1, 2, 3, 4, 5, 6, 7 minus. 1, 2, 3, 4, 5, 6, 7 minus. Now this phosphorus satisfied octet. Now formal charge equal to number of valency electron, number of non-bonded 0 minus half into number of bonded electrons 1, 2, 3, 4, 5, 6, 7, 8. So 5 minus 4 plus 1. This is for phosphorus. And formal charge of oxygen atoms. When you are calculating the formal charge of oxygen atom, you have to write the modern picture of phosphate ion. Number of oxygen atoms 4. So charge minus 1, minus 1, minus 1, 0. Therefore, formal charge of oxygen is equal to minus 1, minus 1, minus 1 plus 0 whole by 4. This is minus 3 by 4 minus 0.75. This is average formal charge of oxygen in PO4 minus 3. Like that you have to approach for all competitive exams. Very important question. This is very important. Here only I am saying bond order. Bond order. Bond order is equal to bond order. Number of bonds. Number of bonds attached to central atom. Central atom whole by number of resonating structures. Number of resonating structures. In this case, P double bond O minus, O minus, O minus. Now, how many bonds are there? 1, 2, 3, 4, 5. Number of resonating structures, 4. So, 1.25. It is bond order. Like that, if you consider carbonate ion, carbon, 1, 2, 2 electrons. Oxygen, 6 electron. Another oxygen, 1, 2, 3, 4, 5, 6. Another oxygen, 1, 2, 3, 4, 5, 6. So, number of bonds, 1, 2, 3, 4 by number of resonating structures, 3, 1.33. Similarly, if you consider benzene, in case of benzene, carbon 1, carbon 2. Now it is having another resonating structure like this. Carbon 1, carbon 2. So another formula of bond order. Bond order also equal to number of bonds. Number of bonds between fixed atoms. Whole by number of resonating structures. Yeah. Bond order have so many formula. number of bonds by number of resonating, number of bonds between the fixed atoms by number of resonating structures. Number of bonds are how many? 1, 2, 3. Total number. Fixed atoms in all resonating structures. Like that. So here 1, 2, 3 by number of resonating structures 2. So 1.5. Yeah. Similarly, if we consider perchlorate ion, Cl double bond O double bond O double bond O O minus. What is the bond order? Bond order is equal to how much? Bond order. Say, bond order is equal to number of bonds. 1, 2, 3, 4, 5, 6, 7 by 4 resonating structures. 1.75. Okay, like that we have to approach. Yes, sir. Yes, sir. Okay, sir. Sure. Yeah. But students are available now.
9:30 వరకు తీసుకుంటారు కదా.
Up to 10 also.
చాప్టర్ అయిపోయిందని చెప్పేసి.
Okay, sir. Right. Yeah. Dear students, I am taking till the end of this chapter because we are having Telangana EAMCET very close to you. So I want to take the class up to 10 o'clock. Now tell me, my dear students, are you willing? If you are not willing, if you are having any other schedule, you watch this video later. Say, Kiran Sai, okay na? Lohit Naveen. Okay, now, yeah, this is about bond order. Bond order done. Now, I want to discuss about, I want to discuss about valency bond theory. Yeah, what is this valency bond theory? According to valency bond theory, a chemical bond is formed by overlapping of atomic orbitals having electrons which are with opposite spin. This is called, what do you call it as? Valency bond theory. According to valency bond theory, there are type of overlappings, SS overlapping. Therefore, 1s more energy than 1s 2p, then 2s, then 2p 2p, then 2s 2p, then 2s 2s. Many are having tension now. Sir, how 1s maximum? We studied pp overlapping is more than sp, than ss. It is only after first shell. Okay, it means 2p 2p greater than 2p 2s. Extent of overlapping is more than 2s 2s. Like that, 3p 3p, then 3p 3d. I'm sorry, 3p 3s, 3p 3s, then 3s 3s. But 1s more than 1s 2p, then 2p 2p. Why? Because it is first shell 1s. It is also first shell. If we consider 1s first shell and 2p, 1s and 2p, of course p orbital, second shell, bond length is longer, short. Therefore, this bond energy more than this comparison to 2p 2p, because 2p 1 and 2 and 2, 1 and 2, here also 1 and 2. So this is 2p. It is also 2p. Bond length is long. Therefore, 1s more than 1s 2p more than 2p 2p. Very important. Now, according to as per VBT, as per valency bond theory, formation of water, oxygen, 1s2, 2s2, 2p4. Okay, now this oxygen atom is there, connected by one p orbital, second p orbital, and third p orbital. Now, these are the p orbitals of oxygen atom. Now, this is connected by s orbital of hydrogen. It is again connected by s orbital of hydrogen. So, these two are perpendicular, bond angle 90 degree. Remaining lone pairs are present in another p orbital and another 2s electrons. So, as per VBT, bond angle of water equal to 90 degrees. Same thing, nitrogen 1, 2, 3. So it is overlapping. All are 90 degrees. So as per VBT, bond angle of ammonia also 90 degrees. Next, formation of methane molecule. Now type of overlapping here, 2p and 1s overlapping. So in ammonia molecule, 2s, 2p, 1s sigma bonds, 3. Like that, if you consider formation of methane, carbon 1s, second shell, this is having one p orbital, second p orbital, third p orbital, this is 2s orbital, right? If you see like this, if we consider 2pz, 2py, 2px, now in the formation of methane, it is overlapping hydrogen, 2p, 1s sigma bond. It is also 2p, 1s sigma bond. It is also 2p, 1s sigma bond. This is 2s sigma bond, 2s 1s, 2s 1s sigma bond. Now tell me what are the types of overlapping in the formation of methane in methane as per VBT 2p comma 1s sigma bonds 3 2s comma 1s sigma bonds 1. Very important question. Understood all of you? Yeah. Now I want to explain formation of molecules deviating from octet rule. I forgot to say before valency bond theory. Before valency bond theory. Now listen. What is that? See, formation of carbon monoxide. Number of electrons in carbon 1, 2, 1, 2, 3, 4. Number of electrons in oxygen 1, 2, 3, 4, 5, 6. So, in this kind of representation, this carbon has only 6 electrons. This oxygen has 8 electrons. So it is not correct. Now carbon 1, 2, sorry. Carbon 1, 2, 3, 4. Oxygen. Now I am writing the electrons of oxygen. 1, 2. Right. 3, 4. And 5, 6. So it is donating. Oxygen acquire partial positive charge, carbon acquire partial negative charge. Therefore, it acts as ligand. Donor is carbon. The formation of coordinate covalent bond. Next, another thing. Calculate total number of valency electrons in the formation of sulfate and phosphate ions. How many? It's very important question. Sulfur 3s2 3p4 6 valency electron. Oxygen 2s2 2p4 6 valency electron. But in SO4 4 oxygen atoms into 4. So 24 electron. It is also 6 electron. And they are saying -2 charge. If they are saying -2 charge, Amma, Kiran Sai, Javed Parvez, understood? Santosh. Okay. Yeah. Now, what I am going to say? -2 charge is there. Therefore, 2 electrons we should add. Total number of electrons, 32 electrons. So, total number of valency electrons, 32. Total number of valence electrons are how many? 32. Very important. Okay. Now, I want to discuss about hybridization and VSEPR theory. Hybridization and VSEPR theory together. Yeah, hybridization and VSEPR theory together. Now, what I am saying now, look, First, whenever you want to find out the number of hybrid orbitals, you should know what are sigma bonds and what are lone pair. That is enough. You can take decision what is the shape like that. If there are two sigma bonds only, linear, shape is linear. Example, beryllium chloride, only 4 electron, incomplete octet, incomplete octet, incomplete octet. Now, if there are 3 sigma bonds, trigonal planar, trigonal planar, 4 sigma bonds only, tetrahedral, done. Like that, 5 tetrahedral means like this. If there are 5 sigma bonds, trigonal bipyramidal, trigonal bipyramidal, right? These are longer, these are longer, these are short. Now, in this trigonal bipyramidal, number of 90 degrees, 1, 2, and 3, this chlorine to this bond, also 90. So, above the plane, above the plane, above 390 degrees, 90 degrees are 3. Similarly, below the plane, number of 90 degrees, also 3. So, total number of 90 degrees, 6. And total number of 180 degrees, this is 180, 2. This side 1, this side again 1. Next, this if you consider PCl5, it is having a picture like this. Now in this PCl5, what I am saying, these are equatorial bonds, 120 degrees, 1, 2, 3, done. If you consider sulfur hexafluoride, sulfur connected by 6 fluorines, like this, like this. So, in this case, here number of 90 degrees, 1, 2, right, 3, 4, plus down again 4, total 8. Number of 90 degrees are above, above, above 4, below 4, on the plane, this is again, it is again 90, like that, on the plane also 90, 4. So total number of 90 degrees are 12. Total number of 180 degrees are how many? 1, 2, 3. Right? So, total number of 180 degrees, 3. If you want to completely explain IIT Advanced like that, total number of 180, 6. Because this is 1, it is also another 180. Like that. So, like this you have to approach. Similarly, now I want to explain formation of PCl5 in solid state. In solid state, it exists as PCl4 plus PCl6 minus. Why? To attain, in order to attain symmetry, it is tetrahedral, having symmetric structure. It is octahedral, also having symmetry. And if you consider PBr5 and Pi5, both are in solid state, exist as PBr4 plus Br minus. Why? Because PBr6 minus does not exist. It will never exist. Why? Because phosphorus small size, bromine have large size. They cannot fit. 6 bromine atoms cannot fit. Therefore, this is the existence in solid state. Pi4 plus I minus. Now, I want to explain. This is only sigma bonds. If there are lone pairs are present, then geometry same, shape will change. Example, if there are 2 sigma and 1 lone pair, SnCl2, angular geometry, dichlorocarbene, also angular geometry. It is 2 sigma bond and 1 lone pair. If there are 3 sigma bonds and 1 lone pair, we consider ammonia a lone pair. If you consider ammonia, not ammonia, nitrogen trifluoride. Now here the bond angle is 107 degree 18 minutes. Here only 102 degrees. Why? Because here nitrogen electronegativity more. So bond pairs close to nitrogen. So repulsions are more. And in NF3, fluorine electronegativity more. So bond pairs close to fluorine. So repulsions are less repulsions of bond pairs. So bond angle is less. Here only I want to explain, here only because NF3, NaH3, dipole moment also. Dipole moment means here nitrogen more electronegative. Bonding is towards nitrogen. Lone pairs are also in the same direction. So bond moment, orbital moment are in same direction. Maximum dipole moment in ammonia, right? Minimum dipole moment in ammonia nitrogen trifluoride. Why? Fluorine more electronegative. So bond pairs are towards fluorine. Here orbital moment is in opposite. Therefore, net dipole moment less. Therefore, dipole moment of NF3 less than dipole moment of ammonia. So, like that we can understand dipole moment. Now, if there are 4 bond pairs and 1 lone pair, there are 4 bond pairs and 1 lone pair, then geometry, seesaw geometry. Why? If we consider sulfur connected by 4 fluorines, there is a lone pair is an equatorial position. Why? Because if lone pairs are present here, the bond angle is 120 degrees. If you consider 2 fluorines, 3 fluorines here, one lone pair is here, another fluorine here. This bond angle 90 degrees. Therefore, repulsions are more. Repulsions more. So less stable. It is only more stable. Similarly, 3 bond pairs, 2 lone pairs. Very important. Here, example, chlorine, one fluorine, another fluorine, another fluorine, and the lone pairs are placed only in equatorial position. This is called equatorial position. Why? Why? Because the bond angles are 120 degrees. 120 degrees. Here also 120 degree. Far. Here also 120 degrees. Far. If you keep this, if you keep the lone pairs here also lone pairs. 3 fluorines in equatorial position. Here the bond angle is 90 degree. Here also 90 degree. 1. How many repulsions are there? 1, 2, and 3. There are 6 repulsions. 6 repulsions. Therefore, ClF3 has bent T shape. Bent T shape, but not this. Understood? But not planar. Next. Now, I want to explain shortcut of hybridization. Like that, if there are 4 bond pairs, 2 lone pairs, wherever you keep, repulsions are same. So, example, formation of xenon tetrafluoride, xenon 1, 2, 3, 4, 4 fluorines, right? One lone pair here, another lone pair here. So, square planar geometry. Even though if you keep lone pair here, 90 degrees only. If you keep lone pair in the axial, so lesser repulsions. So stable. Similarly, like that you can approach. Now, I am saying about shortcut formula. For hybridization. Shortcut formula for hybridization. See, there are 3 or 4 different model shortcuts. Always you follow static number rule. SN rule equal to number of sigma bonds plus number of lone pairs equal to number of hybrid orbitals. Number of hybrid orbitals. Okay, yeah. Jahid Parvez, how are you? Yes. Now, see, my dear students. Now, what I am saying now, number of hybrid orbitals. Yeah. Now, consider, if you consider bromine pentafluoride, mention the hybridization. Central atom is bromine. Bromine has configuration NS2NP5. NS2NP5. So what I am saying now what I am saying, bromine pentafluoride. See, now bromine pentafluoride. Just 1 minute. Bromine pentafluoride.
ఛార్జింగ్ అయిపోయిందా సరిగ్గా ఆపేసేసి
Okay, my dear students, will continue tomorrow. Okay, tomorrow 2 times classes, 5 to 6 as well as 8 to 8:15 to 9:30. Okay, thank you, my dear students. Thank you.